Hi there, folks. Today we're going to be looking at exponential growth. And we've already talked about exponential growth a little bit from the perspective of basic exponential functions. Remember, when we started exponential functions, we started with y equals a times b to the x. And when the function increased as it went left to right, so again, when the function looked like this, we called that exponential growth. The only difference that we're going to make here is that instead of talking about it in terms of x and y, we're going to talk about it in terms of time versus amount. So before it was x is going up and y is going up. Now it's going to be that time is going up, so the amount is going up. All right. It's the same basic concept, but we're going to kind of present this in a little bit of a different format. So exponential growth, an exponential function in which the amount increases as time increases. But again, it's that same thing that we've been dealing with. Remember, the b value was greater than 1. That created exponential growth. And you'll see as we plug these into the different formats for modeling exponential growth that it's still going to be in that format y equals a times b to the x. It's just kind of disguised a little bit. And we'll still see those b values that are greater than 1. Okay? The first model for growth that we're going to look at is the standard model. And I have two different versions of the standard model written here, okay? The first one is kind of like the bare bones minimum version of this thing. And you could get away with using this thing every time, all right? It's a little bit trickier to use this every time because it doesn't have as much information. So this guy right here, this stuff is called kind of grouped together. So this is the format. It's a formula we're going to use, y equals a times 1 plus r raised to the t, where a is the initial amount, R is the growth rate, and T is the time. And there's a couple of quick things here. The rate will usually be given to us as a percentage, but anytime you plug a percentage into an equation, you want to plug it in as a decimal, all right? So make sure you're plugging that thing in as a decimal. That's really important because that's really what a percentage means. A percentage means out of 100, okay? So if you have something that's out of 100, that's going to create a decimal, all right? So 2% would be 0.02. All right, because it's 2 out of 100. And the other thing we have to make sure is we got to make sure all the units match. And that can be a little bit tricky in this bare bones minimum version of this thing. All right, if you have a rate that's 2% per month, then your time must be in months. Okay, if your rate is per day, then your time better be in days. All right, and so that's that first version of this thing. And again, you could use that every time, but it's a little bit tricky making sure the units match. The second version of this guy, let me erase this little. The second version of this guy is really just a modified version of the first thing. So it has all the same elements, but with a little bit extra. So all of this stuff applies to this guy. A is still the initial amount. R is still the growth rate, which we plug in as a decimal. T is still the time, but the difference is that time is now locked into a unit of years. And that's the only difference between these. See, in the first one, we have to worry a lot more about making sure the units match. Well, in the second one, we just have to make sure time is in years. We have to make sure it's in years, and then we just plug in from there, okay? And we'll use this, a great giveaway for especially financial examples when time is in years, is if you see APR listed anywhere. So if you see APR or you see a yearly rate, that means you want to use this second formula. And even though it looks more complicated, the second formula is easier when we're dealing with APR. And I'll give you either of these formulas on the test or quiz, so don't worry about memorizing those. Just understand how to use these things. Again, the first one's the bare bone minimums, and really we'll use that when the time is not in years. As soon as we're talking about APR, as soon as we're talking about time in years, the second formula works out a lot better. And there's one extra element here, and it's this n value. So the n value right here, that's the number of compounds per year. So first of all, compounds, when we're talking about compound interest, when it says something is compounded monthly, essentially the compound is when you're actually getting your increases, when you're getting your money in a financial example, okay? So if it says compounded monthly, it means you're going to get an increase at the end of each month. If it says compounded daily, it means you'll get that increase at the close of each day. If it's compounded yearly, you'll get your interest so at the end of each year. So essentially, you basically don't get any increases until that time frame is up, all right? So again, look for APR, that's annual percentage rate. That tells you that we're talking about years. And then something like if it says compounded monthly, that's the number of compounds per year. Well, there's 12 months in a year, so then N would be 12. If it says compounded quarterly, that means you're going to compound it 4 times per year, so then N would be 4. okay? Compounded daily, n would be 365, okay? So it's just basing this thing on years. So n is the number of compounds per year, okay? The second model for this thing is the continuous model. And we will use this model, first of all, if the problem literally says continuous. There used to be a lot of financial examples that would use this. We don't see those in real life as much anymore. All right, so compounded continuously. If you see that, you'll obviously use the continuous model. So look for that keyword of continuous. All right. The other places that we use this, and really the difference is, the traditional model, the first model we looked at, that is when we have specified time frames for when things are going to be increasing. If we have no control about when the increases happen, if it's increasing all of the time, that means it's continuous exponential growth. And you'll notice down here, we've got A as the initial amount, K is the growth rate constant. Instead of a percentage, a lot of times it's just written as a value, as a decimal, all right? And then T is the time. And so there's one letter up here that's not accounted for. See the letter E up here that's not listed down there? That's because that is not a variable. That's the number E. Remember, E is the natural number. Let me put that in a different color. E is the natural number. It's that 2 point whatever. All right. And I point that out to remind you that if you see the natural number, I want you to start thinking about nature. Because most of the examples that we're going to run into that involve nature, like population growth, like chemical compounds, that kind of stuff, like radioactive isotopes, chemistry type examples, things that occur in nature will be continuous exponential growth. They'll use the one that has the natural number. And so it's an easy way to remember, when should I use this thing? Any kind of biological examples, that kind of stuff, things that appear in nature, okay? Because again, we have no control over when those increases happen. When you look at like population growth, the population is constantly changing all of the time. It's not like the population increases at the end of each month or the end of each year. The population is always increases, always changing, so it's continuous. Okay? For example, if I look at this first guy, it says you have a collector's item worth $1,000. The value increases 2% per month. And notice there's a percentage. It's per month. So that's leading us to believe that this is the standard model. How much is the item worth in 3 years? And notice there's no mention of, per year or APR, that kind of stuff. This is per month. So this is where I want to use that standard, like bare bones model of this thing. So y equals A times 1 plus R raised to the T. And I just start plugging in what I know. A is the initial amount, which is $1,000. 1 plus R is the rate, which is 2%, which I write as a decimal, 0.02. And then T is the time, and here's where we get into that, making sure the units match. Notice, this was 2% per month, but the time is in years. Those units don't match. To make them match, if it's 2% per month, let's convert the years to months. That would be 36 months. And so that's what I plug in here. Since my rate is per month, my time has to be in months. All right? And I'm going to simplify a little bit of this by hand. So we'll do 1,000, and then here that's 1.02 raised to the 36. And I do that for two reasons. One, that's really easy to do, and there's a little bit less I have to punch in my calculator now. But two, now can you see that that is in the format y equals a times b to the x? Okay, it's back to the first thing we ever started with here, where remember a was like the y-intercept, it's the initial amount, it's the starting value, and then b is the thing we're multiplying by, and notice that b value is greater than 1, which makes this exponential growth, okay? And so I want you to understand that this is still the same thing once you simplify and have your equation written in terms of numbers. So now it's just a job for my calculator. I'm going to pull my trusty Casio up. So it's 1,000 times 1.02 raised to the 36. And by simplifying what was in those parentheses, I don't have to worry about putting parentheses into my calculator. If I left this as 1 plus 0.02, I'd have to have that 1 plus 0.02 in parentheses, okay? So I get $2,039.89. And one thing, whenever we're talking about money, I will not tell you how many decimals to round to. You should always round it to 2 decimal places because we're talking about money, okay? All right, in this example, we're depositing $500 in an account that pays 8% APR, that's annual percentage rate, compounded yearly. What is the account balance after 6 years? And I'm going to do this one twice. I'm going to use the bare bones minimum formula, and then I'm going to use that second formula that we would typically use with APR. So in this one, we've got y equals a times 1 plus r raised to the t. And again, I'm going to just plug in what I know here. I know the initial amount is 500. The rate is 8%, so that's 0.08. And again, I have to make sure the units match here. And when we look at this, APR is a yearly percentage. It's compounded yearly, and the time is 6 years. And so essentially all these units already match, so I just plug in the 0.08, and I plug in the 6, and I'm ready to go. And so when you're looking at this, you're probably thinking, well, why would I ever use that other formula? We'll see in a moment. Just got to bear with me here. And so this one, as we simplify, that's a 1.08, and now we can see it in the format y equals a times b to the x again. But now, once again, job for my calculator, it's 500 times 1.08 raised to the 6th power. The reason this one was so easy is because the units already matched, and we'll see what happens when they don't match. So let's see, that's $793.44. Okay. Now let me use that other formula. The other formula is going to seem more complicated in this example, but when you get used to using that formula, it really pays off in the long run. So here we've got y equals, this is going to be a times 1 plus r over n raised to the nt power. And so the initial amount, same thing, the initial amount is a 500. The rate is the 0.08. Notice I'm not even thinking about the time and the making sure that the units match. I'm just plugging away. The time up here is 6, so I can plug a 6 in up here. But now I just have to figure out what n is. N is the number of compounds per year. So if it's compounded yearly, the number of compounds per year is 1. So I plug a 1 in here for n. And now I'm going to simplify a little bit. And yes, you're going to see that I come up with the same thing that I had off to the left here. That's 1 plus, well, 0.08 divided by 1 is 0.08. So when I add that, I get this. And then up here, 1 times 6 is a 6. And now I'm back to what I had over on the other side, which is going to give me the same result, the 793.44. And you're probably looking at that going, well, I'll just use the first version, okay? Well, for this example, of course, the first version was easy because the units already matched. But now let's see what happens when they don't match. So something like this guy, you invest $5,000 in an account that pays 12% APR compounded monthly. So right away, you should realize the units don't match. APR is a yearly percentage, but it's compounded monthly. What will the account balance be after 2 years? Okay, and so if I try to use the bare bones minimum formula, so the initial amount, that's an easy one. That's the 5,000. That's what I start with. And as I go to put this rate down, I should realize, wait a minute, that rate doesn't match the units. It says 12% APR, 12% per year, but compounded monthly. So what I have to do is I have to convert this. I have to make sure the compounded monthly matches the percentage, which is right now a yearly percentage. So what I have to do is take this off to the side and say, okay, if it's 12% per year, what is it per month? And so what I do is I divide by 12. So that means it's like 1% each month. Okay, so it's 1% per month. So instead of using 0.12, instead of using 12% for my rate, I actually have to use 0.01 for my rate. And now when I look at this, see, that makes the units match. Now it's 1% per month, compounded monthly. And now it says the account balance after 2 years. Well, that unit doesn't match either. All right. So I had years, months, and years. Well, now I have months, and I have to convert this 2 years to months, which is 24 in terms of months. Okay, and so it's not that hard, but there's a lot more thinking involved here as I try to plug this in. And now it's just a little bit of simplifying. Once again, I'm just going to do a little bit by hand because I can and because it's easy. And now I plug it into my calculator. So my calculator says to do 5,000 times 1.01 raised to the 24th power, and I get 63.4867. Okay? But now let's check out the other formula. This is where this other formula kind of shines for us. If I start the other formula, it's y equals a times 1 plus r over n raised to the nt. And so now I start plugging in the initial amount is 5,000. The rate is 12%, so 0.12. Notice I'm not even worried about units yet. And the time up here is 2. See, this formula is built for years, so I just plug it in. But now n is the number of compounds per year. So if it's compounded monthly, that means it's going to be compounded 12 times each year because there's 12 months in a year. So I plug a 12 in. And now I simplify. And you see what's about to happen as I simplify this thing. 0.12 divided by 12 is 0.01 plus 1. This is just going to simplify to exactly what I had off to the left. But notice there was a lot less thinking involved. The formula took care of those units for me, so I didn't have to worry nearly as much about the units. That's the advantage of that second formula, okay? So again, I would get used to using that formula when you see APR. All right, it'll make your life a little bit easier for you. This one, same kind of thing. You invest $5,000 in an account that pays 12% APR compounded monthly. How long will it take the account to double? This is the same example, except this time, instead of figuring out how much I'm going to have after a certain amount of time, I'm given the amount that I want, and I have to solve for time. Okay, so I'm going to use that second formula because I think most of us are going to get in the habit of using that. But as I plug this in, the initial amount is 5,000. Got my percent. The n value compounded monthly, so n is 12. And then up here, n is 12 times t, because I don't know what the time is. That's what it's asking me to solve for here. That's an ugly looking t. Let me try again. See, it says right here, how long? It's asking me to find time, but it tells me how much I want this to equal. I want the amount in the account to double. So if I started with 5,000, I want to know when this is going to equal 10,000. And now I'm going to simplify a little bit. Let me simplify everything, and then I'll start solving this guy. So as I looked before, when I simplified this, it gave me this guy. And you could plug that into your calculator. Up here, 12 times t is just 12t. And now let's solve this thing. Remember, solving exponential equations, I just have to isolate the exponential part. So I undo multiplication before I undo the exponents. So I'm going to divide each side by the 5,000. And this goes back to the last thing we were doing. And so that gives me a 2. Over here, I'm going to leave a mysterious space in there because I'm a weirdo. No, I left that space because does everybody hopefully realize how we're going to solve this thing? When you look at something like this guy, we have two methods for solving exponential functions. Getting common bases, which looking at a 2 and a 1.01, that might be a little tough to get common bases. So our other method for solving this is using logarithms. And you could take the natural log of each side. I'll do that in the next lesson. I'll start taking the natural log just to get us used to each of these methods. But remember, when I only have one thing raised to a power, to undo 1.01 to a power, I get to the log of 1.01 because I know those are going to cancel. Whatever I do to one side, I have to do the other side. And so over here, these guys cancel out. So I'm going to be left with the 12t. Over here, I literally have log base 1.01 of 2. And now to solve for t, I divide each side by 12. And again, this becomes a job for my calculator. So as I plug this into my calculator, let's see. Here's how I'd plug it in. Remember, to do log base whatever, I can use my change of base formula. So to do log base 1.01 of 2, I do the natural log of 2. And again, for many of us, don't forget your parentheses around that 2, divided by the natural log of 1.01. So that'll do that logarithm, which gives me that, and then I have to divide that by 12. So I get about 5.8. And again, the nice thing about the formula we just used is that time is always in years. So I know that time comes out in years. Okay. If I'd used the bare bones minimum formula, I'd still get the same thing as long as I'm making sure the units match, but my time would come out in months because I would have converted that percent to months. Then I'd have to convert it back to years. Okay. So use the appropriate formula and you'll be a little bit better off. Okay. All right, in this example, we've got a colony of bacteria that's growing at a growth rate constant of 0.045 per day. And right away, you should notice that instead of giving us a percentage, they said a growth rate constant. That's a giveaway to that we're using that continuous growth model. Plus, this is a biological example. It's a nature type of example. Bacteria occurs in nature, so we're going to use the one that has the natural number. If the colony starts with 100 bacteria cells, how many are there after 5 days? And so this one, again, we've got that A of t, and keep in mind, A of t, that is function notation like f of x. That is not A times t. If you want to use y instead, if you want to call it y equals A times e to the kt, that is fine, just fine. There's nothing wrong with that. Many of you are going to find that maybe a little bit less confusing. But here, I'm just going to leave it as A of t equals A times e to the kt. And remember, A is the initial amount, which in this case is the 100. E is the number E, so I leave that the way it is. K is the 0.045. That's the growth rate constant multiplied by time. And notice here, again, make sure the units match. This was per day. The time is in days. So we're good to go there. So I'd plug that in. I'm using blue. And now this is a job for my calculator. And again, when you're doing this on the calculator, a couple quick things here. One, let me clear that out. If you want to punch this in all in one shot, that's okay. All right, times E, remember your E raised to a power button. You have to put this exponent in parentheses. You have to do 0.045 times the 5 in parentheses if you want to do that all in one shot, okay? So keep that in mind. One of the things that you might want to consider doing is do the 0.045 times 5 on your own. And now write that down or whatever, and then do the 100 times, and then you could do e raised to the power, and then you could punch in that 0.225, or you can do the answer button, which will plug in your previous answer. Okay, and notice it gives you the same thing, but just be aware of that. Make sure that if you're going to punch this all in one shot, use parentheses around that exponent, okay? And I'm going to round this to the nearest whole number because we're talking about bacteria, so I'm going to say 125. And that's it, okay? Yeah, make sure I got it. If I look at the next example, it says the initial population of a species is 36. After 1 day, the population is 46. What is the growth rate constant of the population? So remember, the growth rate constant is the K value. So now I know what I'm supposed to be solving for here. So again, A of t just stands for amount based on time. That is one variable. It is not two variables over here. It's one thing. It's like y equals A times e to the kt. I know that K is the thing I'm solving for, so I have to plug everything else in. Notice the initial population is this 36, so that goes here. K is the thing I'm looking for, and then multiplied by T. T is the time. It says after 1 day, so the time is 1. And it says after 1 day that this is going to equal, tells me the population is going to equal 46, so that's the new amount. See, the initial amount was 36. After 1 day, the new amount equals 46. And so now this is an exponential function that I'm going to solve. Here I divide each side by 36. Remember, I got to get the exponential function by itself. And we can just leave this as a fraction. You can reduce the fraction if you want. That's 23 over 18. I guess I'll reduce it. And now this is e to the k times 1 is just k. But now to undo e raised to a power, this is where I would use the natural log. Remember, natural log is log base e, so if I want to undo e raised to a power, I need to use log base e, which is the natural log. And this is why I told you to get used to using the natural logarithm. It's because it would be more useful in the future. Well, here it is. Natural log and e cancel each other out. So I end up with the natural log of 23 over 8 equals k. And now I just have to plug this into my calculator. If I had k times something, obviously I would divide by that thing here. But here, natural log, and notice, use the parentheses, 23 divided by 18, and then close your parentheses. Parentheses become very important plugging these into the calculator. So I get 0.245. I'll go 3 decimal places. And keep in mind that I should tack a unit onto this because it's always important to make sure units match. For this guy, because time was in days, that means this growth rate constant is per day. And that's important if we're going to use this for anything else, which we are about to in the next example. So the next example, same kind of setup. So it says using the value above, what will the population be after 2 weeks? And so again, we're in the same scenario. We've got the initial population of 36, but now we know the growth rate. So if I jump down here, so I've got A of t equals, the initial amount was 36, times e to the k. I know the k value now is 0.245, multiplied by time, but keep in mind, got to make sure the units match. That k value is per day, so my time has to be in days, so 2 weeks, I have to plug that in as 14 days, okay? And now this becomes a job for my calculator. Once again, if you want to punch that exponent in first, that is fine. If you want to do it all in one shot, you need parentheses around it, so I'll do 36 times e to the parenthesis 0.245 times 14. And it gives me, if I round to the nearest whole number, since it's a population, 1,112. Again, let me show you the other way. One of the other options here, is if you do the 0.245 times the 14, and then you could write that down or whatever. Now do 36 times e raised to that power. Here's the other option. You hit second and then that ANS. And basically, it just used whatever your previous answer. And so it plugs that 3.43 in, or you can type in that 4.343. Notice I get the same answer. So 1,112. So it's all the same stuff that we've been doing, but now we're applying it to a specific situation. We're applying it to actual examples of exponential growth that we might run into in real life. Okay?